In this video, we are going to talk about how to use elimination to solve systems of differential equations. Um, it is similar to the process of solving a system of linear equations from algebra. So what I want you to do first is solve this system in two ways. First, by elimination, and second, by substitution. So do both ways. I'll hit pause, and I want you to hit pause as well. Do it, and then we'll come back and check your work. Here come the answers. So elimination is done in blue, and substitution is done here in purple. When I have elimination, what I do is I multiply this row by -5. At least that's the way that I think it's the easiest here. And then I can add the two, add this to this line, because it's just rewritten. I get 17x equals -51, divide, get x equals -3, and then I got to figure out how to get y. So in this case, I took this equation over here. I got a y. Since I know x is -3, I can plug it in there and subtract -2. So I get -3 and 2. When I do substitution, I solve for one variable in one of the equations. So when looking at this one, I'm definitely going to go with that y here because it doesn't give me any fractions and it's easiest to solve for. Get y equals 2x plus 8. Plug that in here, do some algebra, and look, this line right here is the same as this line right here. And notice that I got to this line, I got to this line right here by adding -40 and -11, and here I got -11, -40, blah, blah, blah. What I wind up doing is dividing, getting x equals 3, and then I take this guy back in, and I get my 2. What I was trying to say with the -40 and the 11 is that essentially we're doing all the same math with these, we're just organizing it in a different way. And that's the way a lot of these solution methods are. So, systems of differential equations. So the first thing I need to do is show you what a system of differential equations is, and then I'm going to show you how to use elimination to solve that system. Now, from the get-go, I will tell you that elimination, when we are solving a system of differential equations, does not look like this. It looks much more like this. So maybe substitution would be a better name, but it's typically called elimination. So you'll see that as we go along. I won't dwell on that for too long. So differential equations. I'm going to write a handful out here. So I've put 3 second-order differential equations here. X double prime minus 3x prime plus 2x equals 0. The same thing equal to sine of t. And then this one, which is x double prime minus x prime squared plus 4x equals 0. A couple things that I want to point out. First, x prime is now fixed. It's not dy dt. X prime is dx dt, is the rate of change of x with respect to time. We can have linear and nonlinear. Can you tell which ones here are linear and which ones are nonlinear? This one's linear, this one's linear, this one's nonlinear because the x prime is squared. And then I can have inputs or external forces. So this sine of t is an input for this equation. We can have all the same types of things with systems. We can have linear and nonlinear systems, and we can have inputs in these things. For now, we're just going to focus on linear systems, and every time I talk about a derivative, it's always the derivative with respect to time. And before I show you an example, I want you to solve this thing right here using methods that you know from previous points in the differential equations course. I'm going to pause. I want you to pause too and solve it. Here comes the answer. So we typically go straight from this to the characteristic equation. I'm not going to reteach why that's true, but it is because we use a trial solution of e to the rt. And then I could factor that. R minus 2, R minus 1 gives me 1 and 2 for my R values. And then that gives me x equals c1 e to the t plus c2 e to the 2t. So you should be familiar with that, and you should be good with that, and it connects to what we're going to do next. So now I'm ready to show you what a system of differential equations looks like. I have x prime equals 4x plus 2y, and y prime equals negative 3x minus y. This is a system because, you know, they're tied together just like the systems of equations above, and it's a system of differential equations because this is a differential equation. It's an equation with a derivative in it. And remember, this x prime is it's a derivative with respect to t. Same with the y prime. It's a derivative with respect to t. So I want to solve this thing. So what I need to do is reduce it down to one variable. That's probably why we call it elimination, because we are eliminating one variable. But it does look a lot like substitution from above. So what I need to do is solve for y in this equation. Why do I solve for y in this equation? Because if I do that, I've got y in terms of just x's. The other thing I could do is solve for x in this equation and just have x in terms of y's, and that would work as well. I guess I should also add that there is tons of context to these equations. For now, we're just going to talk about how to solve them, and we'll jump into the context as we move along. Okay, so if I solve for y, I get y equals, I'll do everything at once. So I get x prime over 2 minus 2x. All I did was move this over and divide by 2. So from there, what I can do is take the derivative. Y prime is equal to x double prime, because it's just with respect to time. So there's no quotient rule or anything here, over 2 minus 2x prime. So from here, what I want you to see is that I can sub this y here in right there, and I can sub the y prime in right here. And notice what I'm going to get is all x's. So I'm eliminating the y, why we call it elimination. So if I do that, I get, all right, so y prime first is, so I'm going to write this, x double prime over 2 minus 2x prime, and then equals, then I got my minus 3x right there, and then minus y. So minus this thing. So I'm going to go minus x prime over 2, apply that negative in, don't miss the double negative there, plus 2x. So first thing I sort of look at here is the fractions. I don't like them, so I'm going to get rid of them. I'm going to double everything. What's that give me? X double prime minus 4x prime equals negative 6x minus x prime plus, not 2x, plus 4x. So from there, I'm going to move everything over to one side. All right, how many x? I got x double prime. All right, I got minus 4x prime here. And then I'm going to add this. So that gives me minus 3x prime. And then I got minus 6x plus 4x. That's minus 2x. Move it over to the other side. I get plus 2x. And that is equal to 0. Oh, snap. That's the one that we just did up here, isn't it? So we know the solution to that. You would just do your regular characteristic equation. We know that x is c1 e to the t plus c2 e to the 2t. So we solve that thing the way we'd normally solve a regular second order linear differential equation. And now what I can do is use this equation right here. Now that I know what x is, I remember originally had y in terms of x's. So if I were to sort of equate this to what we did up above, at this point I've solved for the x here, and I need to go and this is the line that I had there with y's at y in terms of x and x prime, and I need to plug that stuff in. So I think it's more like substitution than it is like elimination from old school. So let's bring this down here, and I need to have x prime over 2 minus 2x. So I need to find x prime. That is c1 e to the t, because that derives to itself, plus 2, chain rule, c2 e to the 2t. So when I do my y using this, I'm going to do y is equal to, all right, x prime over 2. That is this divided by 2. So that is 1 half c1 e to the t, oops, plus half of that just gives me c2 e to the 2t. And then what I have, minus 2 times all this. So I'll distribute that negative 2 in. I get minus 2c1 e to the t minus 2c2 e to the 2t. And I could begin to simplify this. All right, I have c1 and a c1 e to the t. So actually I have negative 3 halves c1 e to the t. That was this one and this one. And then I have minus, all right, I have minus 2c2 plus, so minus c2 e to the 2t. And from there, I have my solution, remember, right? Like I'm looking for x prime equals this, y prime equals this. What would my solution be? It would be a x equals and a y equals function of t. So notice I've got this guy right here. Which I can paste like that. And then I can say, green, y equals negative 3 halves c, I'm going to give myself a little e to the t minus c2 e to the 2t. And that is the solution to this system of differential equations. Again, these have tons of applications and meanings, but for now, we're just working on how to find the solutions. So here's the problem with these. There are actually an infinite number of correct solutions. For example, if you instead had solved for, here I solved for y in this one. I said earlier, you could have solved for x in this one. You would have gotten a different equation. What you would have gotten was, well, I guess that what you would have been most likely to get would have been y equals, this one would have been the c1 e to the t plus c2 e to the 2t, and my x would have been like the inverted version of what I have up there. So it would have been negative 2/3 c1 e to the t, and then minus c2 e to the 3t. So I think that as we move along, you'll see why that is true. But these answers can take an infinite number of correct forms. Although I think that these two are the two that you are most likely to run into doing this method. The last thing I'd like to show is another way to write this form right here. I can write it using matrices or vectors. I can write xy equals, see that both of these terms have an e to the t? So I'm going to write an e to the t. And then I'm going to write a little vector like that. And then see that they both have a c1. So I'm going to put my c1 here. And then notice if I put a 1 here, then as I follow across, x equals, the c1 gets multiplied by the 1 and then the e to the t and gives me this term right here. And then I write negative 3 halves here, and then the y would be equal to the c1 times this times that, which would give me this. Plus, let's see if you can guess what goes right there. I get an e to the 2t here, and I get a 1 and a negative 1. And when we learn other ways to solve these things, we're going to have methods that seem totally different that get us straight to these values instead of going through this long, long mess right here. And these things have special names that we'll talk about later. I'm going to do one more video related to this stuff, so it'll be linked. See ya.